Hello, this is Dr. Lukes. This is Lab 11 and our last week for numerical computing. We are going to be looking at higher order ordinary differential equations and the Runge-Kutta method, how we can do that to solve initial value problems. So to solve a higher order IVP using this method, what we want to do is recast it as a system of ordinary differential equations. So an nth order ordinary differential equation is going to become a system of n equations and n unknowns. So we'll just look at a second order. That's enough to get the idea. But what we're going to do is set z equal to the penultimate derivative of y. So in the case of a second order, it would be the first derivative. And we can solve for two derivatives, so dy dx is going to be a new variable z, and dz dx, the second derivative, is equal to some number times the first derivative and some number times the constant, and possibly you even have the independent variable in there. Anyway, the Runge-Kutta method then, what it does is it comes up with how to evaluate these to get a good estimate. And so we can go through all these formulas, lots and lots of formulas. Again, like we did with the Runge-Kutta for a first order, once you program it one time, just save that file and it's good for forever. So these are all the little snippets you need to put together to solve for your y and z as you go through the calculations. One of the things that I really recommend is just start by practicing the setup. And so, for instance, if we have here a first order initial value problem, right, y of 0 is 2, then I can take this and solve for the derivative y prime equals. And so that's going to be, if we look at that, derivative equals the exponential of negative 2t minus the y, and then divide by 2, right? Just solving for that derivative. And then you can use that with this initial value to figure out then what the answer is for y when, say, time equals 3 or something like that. And I'll let you practice that on your own, but this is the key thing that you know how to do. If we have a second order ordinary differential equation, such as this one, y double prime minus 4y prime plus 4y equals 3 sine of t, with y of 0 and y prime of 0 both equal to 1. Well, then we need to set up two derivatives for two equations. So the first one is going to be our y prime, and we're just going to give it a new dummy variable name, so z, for instance. The second one is going to be for the y double prime, and we're going to take this equation and rearrange it. So in that case, what we get is deriv 1 equals z, and deriv 2 is going to be solving for y prime prime, and that's going to be 4z negative 4y equals or plus 3 sine of 2t. So we have this here. And of course, now then we're going to recast those initial values as y of 0 equals 1, and instead of y prime of 0 equals 1, z of 0 is equal to 1. And again, you can solve this for, say, when time is equal to 1. And the cool thing about this one is it's got an actual solution, so you can compare and see that they actually should be very close. Okay, so these are some to practice. What I'm going to have you do for lab, though, is one where we have a system of ordinary differential equations. Now, there are lots of cases where that could happen, and in chemical engineering probably it's something like a system of chemical reactions. That's a very common one that leads to a system of differential equations. And so this is an example that you can come up with where each of these concentrations, the little brackets there mean that, okay, are all functions of all of the other compounds, concentrations. And so we end up with a system of differential equations that needs to be solved simultaneously. We're going to do a different problem. This is a classic predator-prey problem. So it's the Lotka-Volterra model, And basically they talk about the population of a predator such as a wildcat and prey such as rabbits, right? So the wildcat will eat the rabbits. If there are too many wildcats, then they eat all the rabbits, and then the wildcats get hungry, and so they start declining. If you end up with too many rabbits, though, then they eat all of the grass around them, and so then they start dying off. So we've always got this fluctuation of the population sizes. And so this is a model for that. Now, the numbers you're going to get here, maybe if you imagine these as being thousands, where X and Y are thousands of wildcats or thousands of rabbits, maybe the numbers might make sense. But we're just going to use it with whole numbers. So if y prime is negative 2y plus 3xy, so that's going to be my deriv 1 equals. Deriv 2 equals 2x minus xy, and these are my conditions, then I can solve for x and y over a period of time. And so if you go through and look at this for time 1, time 2, time 3, and you see that the fluctuating populations of the wildcats y and the rabbits x. Now I'm going to show you my code. So this is how I set it up. So I read all the various values in. I set up my step size. Okay, B and A were read in up here. And then time is starting at point A. So maybe that's 1 if I'm starting at time 1. Maybe it's 0 if I'm starting at time 0. And then the X and Y value. So that's my starting population. Okay. Then I need to go through the loop. And so the loop is doing the Runge-Kutta method. Now I have set this up one time. I will never have to set it up again because I'm not ever changing this. Okay? Never change this. And so all of this part is just the Runge-Kutta calculation. I've made sure that I have cast everything in the previous steps so that T, X, Y are all known values. Okay? Step size, a known value. And I can go through and do the calculations and change the times and finish the loop. Now the key thing is I need to know what deriv 1 and deriv 2 are. And so those are my functions. And so here are my functions. This was equation 1. This was equation 2. At this point I should be able to run this. It'll print out all of my various populations, X and Y, for various times. And again, I could create a graph of this, or I can just look at the values and watch them fluctuate over time. So for your homework for lab, I want you to just recreate this last little set of code here. And I'll have a separate video where we review for the final exam. Thank you very much.